Welcome to this explainer. If you've ever felt like you're just throwing words at an AI model and crossing your fingers, hoping for the right response, this is exactly what you need to hear. Today, we're going to transform what has long been considered the dark art of prompt engineering into a rigorous, measurable science by exploring a fascinating new mathematical framework for understanding adjectival steering. Think about it. If you're building pipelines using large language models, you absolutely know the frustrating unpredictability of tweaking a prompt and just kind of hoping for the best. You change the word helpful to exceedingly helpful, and boom, your strict JSON output completely breaks, or the model starts hallucinating facts it previously got right. Up until now, prompt engineering has heavily relied on these anecdotal heuristics. It's basically been an era of vibe checks, right? You tweak, run a few manual tests, see if it looks okay, and ship it. But what if we didn't have to guess? What if we could actually measure the exact atomic impact of a single word? Here is our roadmap for this explainer. We'll start with the prompt engineering problem, then look at measuring with Shapley values, how model lineage drives sensitivity, why position and syntax matter, the complex interactions created by scaling, and finally, new rules for developers. All right, let's dive right into section 1, the prompt engineering issue and the control problem. Let's look at why reliable control of LLMs has been so incredibly difficult. We are finally moving away from anecdotal guessing and entering an era of exact quantification. This new research completely replaces that outdated workflow of iterative tweaking with a rigorous mathematical framework. The researchers actually set out to quantify the exact effect of individual adjectives on model accuracy. And they didn't just use a handful of custom test prompts. No, they evaluated 100 distinct adjectives against the massive MMLU benchmark. If you aren't familiar, the MMLU is essentially the gold standard for testing an AI's knowledge and problem-solving abilities across dozens of academic and professional subjects. By running this test with systematically varied adjectives, we can finally stop assuming a word works and start proving exactly how much it moves the needle on complex logic tasks. Which brings us to section 2, Shapley values and measuring the unknown. To actually solve this attribution problem, researchers had to turn to some complex mathematics. They utilize something called Shapley values. Now, if you're not a math person, don't worry, it's a game-theoretic baseline for feature attribution. Let's make this concrete. Think of the adjectives in your prompt as individual players on a sports team. Sometimes the team wins, meaning your model outputs highly accurate, high-quality data. But how do you know exactly how much credit one specific player, say the word expert or concise, actually deserves for that win? Were they the MVP, or were they just riding the bench while other words did the heavy lifting? Shapley values let us measure exactly how much a single modifier contributes to the overall accuracy of the model's output, isolating its specific marginal impact regardless of whatever else is going on in the prompt. Let's slow down and look at the actual methodology here, because it's honestly brilliant. Step 1 involves generating a massive array of prompt permutations. From there, they move to steps 2 and 3, which involve systematically masking and then unmasking those 100 distinct adjectives across all the permutations. Finally, step 4 is where the math really shines. By doing this massive masking and unmasking process over and over, they isolate each word's marginal contribution to the final output. This means developers can finally track exact accuracy shifts. Imagine knowing that adding the word concise to your prompt reliably increases your reasoning accuracy by exactly 1.2% on a specific task, while the word creative drops it by 0.5%. You get a concrete mathematical number. To ensure this wasn't just a fluke on a single model, the researchers evaluated this exact framework across 5 distinct major architectures. They tested OpenAI's O3 and GPT-4o Mini, Microsoft's Phi 3, Meta's Llama 3 70B, and DeepSeek R1. It's crucial to understand why they chose these. They represent a very deliberate mix of massive closed-source powerhouses and nimble open-weight models. By testing across this diverse ecosystem and spanning radically different parameter counts, they proved these findings aren't just quirks of one specific AI's training run, but fundamental truths about how LLMs process language structurally. Let's move to section 3, model lineage and family effects in AI. This is where we uncover our first major plot twist in the research. What the cross-model analysis revealed is a really pronounced family effect. Models trained on shared lineage basically have a shared underlying DNA in how they map language to concepts. If you stay within a shared lineage, like upgrading from GPT 3.5 to GPT 4o, the steering sensitivity of your adjectives remains highly correlated. Your prompting strategy is pretty portable. But that correlation drops sharply. It effectively hits 0 when moving from an OpenAI variant to a distinct lineage like Meta or DeepSeek. This completely shatters the myth of the master prompt. The idea that you can write one perfect system prompt and blindly route it to whatever model is cheapest today is mathematically flawed. If you swap models across lineages, your adjectives require complete recalibration.
Which leads us perfectly into Section 4, Position and Syntax, where you say it matters. Our second twist reveals that it's not simply what you say, but exactly where you insert it. The study demonstrates that steering direction is absolutely not intrinsic to the adjective itself. The exact same lexical token, literally the identical word, produces totally divergent accuracy shifts depending entirely on its syntactic context. If you move a modifier from a system instruction down into a user message or shift it from the subject of a sentence to the object, the steering outcome can literally flip. A word that reliably increased reasoning accuracy in the system prompt might actively degrade performance if you append it to the user data. Why? Because of how attention mechanisms work under the hood. The model weights tokens in a sequence based on their proximity and grammatical relationship to the core instruction versus the payload data. The model isn't just reading your words, it's mapping their structural hierarchy. And this brilliantly illustrates our next major takeaway, captured perfectly by the researchers here. Prompt structure must be treated as versioned code. Because this positional sensitivity is so extreme, a minor, seemingly innocent reordering of your prompt components by a well-meaning developer can completely break previously stable steering patterns. You can no longer treat adjectives as isolated weight modifiers that you can just sprinkle anywhere. Their impact is emergent from their specific structural slot. If you're building CI/CD pipelines for your AI applications, failing to track the exact token positions of your modifiers is going to lead to silent, cascading failures in production. Moving on to Section 5, Scaling Interactions. Size breaks assumptions. Our third twist hits when we look at how model parameter size changes the rules. What happens when multiple adjectives interact as you scale up? Well, scaling introduces immense compositional complexity. Smaller models, like Phi-3, exhibit a much more literal response. They treat modifiers independently. It's essentially simple addition, predictable, but the steering is relatively shallow. But larger models, like the GPT-4 class, show profound non-additive interactions. The deep layers of attention mechanisms start modeling higher-order dependencies between words. This means two adjectives together might synergistically amplify each other, or worse, antagonistically dampen each other. For example, if you combine the word creative with the word strict, you don't get a perfectly balanced output. In a large model, those conflicting vectors cause emergent, unpredictable behavior that can completely derail the logic. You simply cannot expect the exact sum of their individual effects. So we arrive at Section 6, New Developer Rules, Adapting Your Pipelines. The crucial point of this entire explainer is, how do you actually change your production workflow based on this massive paradigm shift? If your production pipeline routes live user queries to LLMs, you must implement these adjustments immediately. First, you need to audit your adjective slots explicitly. Map exactly where the modifiers sit in the syntax tree. Second, expect non-additivity. You must benchmark the full combination of words in your prompt, not just single additions, because large models blend them unpredictably. Third, drop the universal templates. You've got to use model-specific adapter layers if you route queries between OpenAI, Meta, and DeepSeek, because their lineages react differently to the same words. Fourth, version your prompts like software, tracking exact token positions alongside accuracy metrics in your automated evaluations. And finally, you don't have to build this math from scratch. You can automate your feature attribution using the exact Shapley-based scripts the researchers have made freely available on arXiv. We'll leave you with this final, provocative thought. As models continue to scale into the trillions of parameters, their internal interpretation of our prompts is shifting further and further toward unpredictable, higher-order, non-linear dependencies. The simple days of just asking a model nicely or tweaking a few adjectives and checking the vibe are officially over. So as these hidden internal interactions become even more profoundly complex, how will we adapt our engineering practices to maintain genuine mathematical control over the AI systems of the future? Thank you for joining me for this explainer, and I hope this deeper understanding of prompt steering helps you build better, more rigorous systems.